Okay, now we talk about section 3.7. This is where we talk about rational functions. Sorry. Oh, that's too dark. Okay, so in 3.7 we talk rational functions, and I should give you a definition about what a rational function is. Hopefully this will autofocus. There we go. Okay, so by definition, when we're talking about a rational function come in the form so it is a function, so we'll denote it that way. F of x is equal to, and usually we say some p of x over some q of x. So what we're saying here is the numerator is a function of x, and the denominator is a function of x. And where p and q are polynomials, and we also have to put the restriction on it that our function, our denominator function, cannot equal 0. It's the same as a rational number. If there's a value of x that will make this denominator go to 0, we'll get a division by 0, which is undefined, which is a problem for rational numbers, and therefore a problem for rational functions. So, for example, let's review what we've already talked about. Let's find domain. So our first example, let's say f of x is equal to 2x minus 1 over x plus 3. This fits the definition of a rational function. Our numerator is a polynomial, as well as our denominator is a polynomial. So the domain will be everything but what makes the denominator 0. If we're unclear about that, we can always take the denominator and set it equal to 0. Because we know that's what x cannot equal. Solving this, we find that x cannot equal 3. So we could write that the domain is the set of all x such that, and this is the bar that means such that, x cannot equal negative 3. This would be our domain. On the number line, that would say, here's negative 3. I cannot equal that, so I put it with an open circle. But everything else to the left and right is okay. Remembering this is negative infinity on the number line, and this is positive infinity on the number line, then this interval is represented by negative infinity to negative 3, but I can't include negative 3. And then I union it with this interval, which is negative 3 to infinity. Another example, we could have g of x is equal to x plus 7 over x squared minus 25. Again, this fits the definition of a rational function. The numerator is a polynomial. The denominator is a polynomial. So to find domain, I just need to find the values that will make the denominator equal to 0, and then I will exclude them. And we can solve this equation in our sleep. This is x squared is equal to 25. So taking the square root, x is equal to plus or minus 5. This is what x cannot equal. We will exclude those. On the number line, now I have two numbers to exclude, the negative 5 and the positive 5. But every other number is good. So now I have, remembering this is negative infinity and this is positive infinity, I have 1, 2, 3 intervals that I need to include. This first interval goes from negative infinity to negative 5, not including. The second interval starts at negative 5, which I don't include, and goes all the way up to positive 5. Again, not included. And our third interval, I'll put the u down because that just means a union or and for intervals. We start at 5, and then every number up until infinity is included. So this is the domain. Okay, so that's the domain and the basic ideas of rational functions. What we should look at is our basic, our parent function, or our toolkit function. It's all saying the same thing of 1 over x. So together, let's create a table of values for 1 over x. So let's consider a few things. If our function is 1 over x, our basic function, if x is equal to 0, then we get 1 over 0, and we know this to be undefined. We could fill that in over here as well. And what happens at an undefined value in a rational function is that we'll get something called an asymptote, and we denote asymptotes as straight lines that are dashed. So anytime x is equal to 0, it will become undefined. And this is what I mean by labeling the equation of the asymptote. And let's skip down here. Now, this is broken up into considering numbers that are smaller than 1 and getting closer and closer and closer to 0. After this point, the numbers are getting larger and larger and larger and moving away from 1. So in this case, when x is 1, we get 1 over 1, and that's equal to just 1. So we get this point 1, 1. At 2, I get the value of 1/2. At 4, I would get the value of 1/4. At 10, I have a 1/10. And at 100, we have 1/100th. At 1,000, we'd have 1/1,000. Okay. And so something very bizarre is happening. Let me scratch this out. I want to consider what's happening as x scratching this out. So as we are letting x get larger and larger and larger, that is, as we're letting x go to infinity, my question is, what is happening to the function values? Are they approaching anything? So in this column, we have the function values. Okay? If you want to convert these to decimals, you can. This is 0.5. This is 0.25. This is 0.1. This is 0.01. 0.001. So as x is getting larger, the function values themselves are getting smaller. And they're getting so small, one can imagine 1 over a million. This is going to be very, very small. Or even 1 over a billion. We'll have 0.0000000. How many zeros? 1. And so what is happening to the function is that we can say that the function is going to 0. Now, it's never going to get to 0, but it is approaching 0. Now, the fact that this function will never get to 0 means that there's also another asymptote. Okay. So our y's, which are equal to our f of x values, the function as x gets larger from 1 is approaching 0, but it never gets there. And we can label this as the function, or the asymptote is y, which remember is our f of x, is equal to 0. So not only does this function have a vertical asymptote, it has a horizontal asymptote. But this is what happens just as we looked as x got larger than 1 and went on to infinity. We're unclear what's going to happen in between this value of 1 and 0. So to do that, I've examined these values, 0.1, 0.001, etc., etc., which are approaching 0 from the right-hand side and getting closer and closer to 0. So I could substitute these in. I'll get 1 divided by 0.1. But let's think about that instead of 0.1 as 1 over 10. When this happens, I'm dividing fractions. So this is the same thing as the numerator multiplied by the reciprocal of the denominator. And so we have at 1/10, the function itself is equal to 10. Let's continue doing this. I could substitute in 0.01, which is equal to 1 divided by 1 over 100, which once we take the reciprocal is 1 times 100 over 1, which is just 100. Continuing on, now this is the tenths, hundredths, thousandths, so this is equal to 1 divided by 1 over 1,000, which, dividing fractions, I invert and multiply, so this is 1,000. To save room here, this is tens, hundredths, thousandths, 10,000ths. So this is 1 over 10,000. So I'll take 1 divided by that 1 over 10,000. And by inverting and multiplying, we see that the function value there is 10,000. Which is curious behavior. So this is where we've asked ourselves, what is happening as x is going to 0, and this little symbol here means from the right. So here I'm to the right of 0, and I pick numbers smaller and smaller and smaller until they get to 0. Well, they will never get to 0 because we have the x-axis asymptote there. But as I'm getting closer and closer and closer and closer, coming from the right of it, approaching it, the function values are getting larger and larger and larger. So what we can say here then, as x goes to infinity from the right, f of x is taking off to positive infinity. And that is why we can draw the graph taking off like this. Let's look at the same thing on the other side. We have the same demarcation, because notice we've just looked at what happens on positive values of x. Right? So we'll look for negative values. Again, we could do the same substitution, except with the negative values. So this would be negative 1, negative 2, negative 4, negative 10, negative 100, negative 1,000. And we can convert these to decimals. Again, we would have 1, 0.5, 0.25, 0.10, 0.01, 0.001. The only thing, which are the same values we have here, but the difference is these are negatives. So in that case, again we have the point negative, well, we have a corresponding point, negative 1, negative 1. Let's label that here. And now we look. As x is going to negative infinity, that is, as it was getting more and more negative, the function is actually getting less and less negative. You can imagine at negative a billion, we'd have negative 0.000000. How many zeros? 1. And so the function is still going to 0. It's just that it's coming at it from below. So as I come out to negative infinity, the function is getting less and less negative as it approaches, the function approaches 0. Again, we can do the same thing now because we worried about this little area. What happens is I approach 0 now from the negative side. And again, we could go through the same process. The only thing we'd be changing is the negative. Everything else would stay the same. So we could say that this would be negative 10, negative 100, negative 1,000, and negative 10,000. So by looking at these numbers, that is this notation. We are looking at what happens as x goes to 0, and this, the negative sign, means from the left. And as x goes to 0 from the left-hand side, what happens then is that my numbers get larger and larger and larger and more negative. So the function looks like this and takes off to negative infinity as x approaches 0 from the right, or from the left, I'm sorry. I hope this makes sense, and I hope the shape of this function makes more sense to you now. Okay. Now, what we need to talk about is, in a pre-calculus sense, we need to be able to describe these notations. So, what we are saying here is we're really talking about a limit. So what we are talking about is, that is when the limit as x goes to infinity of our function, which in this case happens to be f of x, well, when x went to infinity, the function equaled 0. Okay. So that's this corresponding notation. As x goes to infinity, f of x went to 0. We also had the left-hand notation. We could have said the limit as x goes to negative infinity of our function, which happens to be at 1 over x, also equals 0. Okay. So no matter what value of x, either in the negative direction or in the positive direction, the function was approaching 0, and hence we had this horizontal asymptote y equals 0. But we also had, we looked at the behavior when x went to 0 from the right of our function. And we also have, we described the behavior as x went to 0 from the left of our function. In both ways, we can describe this as a limit. And from here, we saw that as x went to 0 from the right, so here's the right-hand side, the function was taking off to positive infinity. Alternatively, when it was from the left, as we approached x, as x approached 0 from the left, the function dove to negative infinity. So we could say it like this, that the limit as x goes to 0 from the right of 1 over x is positive infinity, while the limit as x goes to 0 from the left of 1 over x is negative infinity. So these are these two limits, as we talk about positive and negative infinity, really talk about the end behavior of the graph, which we will talk about more. There's also this thing called a limit. We could just write it without the plus or minus. In this case, we would be asking about the total limit. This is a left-sided limit. I'm sorry, this is the right-sided limit, this is the left-sided limit. And in this case, we'd be asking about what the actual limit of the function is, not just one-sided. And I hope it stands to reason that this answer should be a combination of these two. And what will happen in this case is we will say there's a problem because the right-hand limit and the left-hand limit don't exist. and so therefore the total limit does not exist. We will talk about this more. Okay. Does not exist, I also abbreviate DNE. You should recreate this activity that we just did and do it for 1 over x squared. Okay, so now let's try and put all this together with an example. Let's say, for example, we have f of x is equal to 5x plus 2 over x minus 4. Let's consider the domain here. Okay, so our domain comes if the denominator equals 0. So we have x minus 4 equals 0. That will happen if x equals 4. So we will exclude 4. And our domain will be the set of all x, such that x cannot equal 4. What that will imply for us then is that when x does equal 4, we will get a vertical asymptote. Okay. So from domain, we can determine vertical asymptote. Okay. Lots of times I'll just say the VA. Okay. And it's important that we remember what the equation is. So the vertical asymptote happens at the restricted value when x equals 4. Now we could ask ourselves, does this function have a horizontal asymptote? Our basic toolkit function did. So it stands to reason that we would probably also have a horizontal asymptote in this case. Now horizontal asymptotes deal with end behavior. Okay? They talk about the limits. So what we're really asking here is what is the limit as x goes to infinity